Imagine a world built from tiny invisible blocks, too small for the eye to see. These blocks, the atoms, are the fundamental building blocks of everything we know. They make up the air we breathe, the water we drink, and even our own bodies. Unveiling the atom, understanding its secrets, has been a long and fascinating journey, a quest driven by human curiosity and the desire to understand the universe. The concept of the atom has intrigued thinkers for centuries. It's a story of brilliant minds, groundbreaking experiments, and revolutionary discoveries. It's a journey through time, starting from ancient Greek philosophers who first imagined the existence of atoms to the modern scientists who continue to unravel their complexities. This essay delves into the captivating history of atomic discovery. We will explore the key figures who shaped this field, from Democritus to Bohr, and the landmark experiments that revolutionized our understanding of matter. Join us as we unveil the atom piece by piece, revealing the secrets of this fundamental building block of the universe. The idea of the atom first emerged in ancient Greece, around the 5th century BC. Philosophers like Leucippus and his student Democritus proposed that all matter was composed of tiny indivisible particles they called atomos, meaning uncuttable. They believed that atoms were eternal, unchanging, and differed in size and shape. Democritus envisioned a world where atoms moved randomly in a void, colliding and combining to form the objects we see. This idea, though revolutionary for its time, lacked experimental evidence and was largely overshadowed by other philosophical schools. Aristotle, a prominent philosopher of that era, favored the idea of 4 elements: earth, air, fire, and water, as the fundamental components of matter. Despite its lack of acceptance, the concept of atomism planted a seed that would later blossom into a scientific revolution. Centuries later, the idea of indivisible particles forming the basis of all matter would re-emerge, this time with scientific evidence to support it. For centuries, the idea of atoms remained dormant. It wasn't until the 19th century that the English chemist John Dalton resurrected the concept, transforming it into a scientific theory. Dalton's atomic theory, published in 1808, marked a turning point in our understanding of matter. Based on his experiments with gases and chemical reactions, Dalton proposed several key postulates. All matter is composed of atoms, which are indivisible and indestructible particles. Atoms of a given element are identical in size, mass, and chemical properties. Atoms of different elements have different properties. Compounds are formed by the combination of 2 or more different kinds of atoms. Dalton's theory revolutionized chemistry. It provided a framework for understanding chemical reactions and the composition of matter. It explained why elements always react in fixed ratios and laid the foundation for the development of the periodic table. Dalton's atomic theory, though groundbreaking, portrayed atoms as solid, indivisible spheres. This view began to change in the late 19th century with the discovery of the electron. In 1897, the British physicist J.J. Thomson conducted experiments with cathode rays, streams of electrons emitted by a negatively charged electrode. Thomson's experiments demonstrated that atoms were not indivisible but contained smaller, negatively charged particles. He proposed a model of the atom, often called the plum pudding model, where electrons were embedded in a positively charged sphere. This marked the first step towards understanding the internal structure of the atom. The discovery of the electron revolutionized our understanding of electricity and magnetism. It paved the way for the development of electronics and ushered in a new era of atomic research focused on unraveling the atom's internal secrets. While Thomson's model provided valuable insights, it was soon challenged by the groundbreaking experiments of Ernest Rutherford, a New Zealand-born physicist. In 1911, Rutherford and his colleagues conducted the famous gold foil experiment, which led to a dramatic shift in our understanding of the atom. In this experiment, a beam of alpha particles, positively charged particles emitted by radioactive materials, was directed at a thin gold foil. Rutherford expected the particles to pass through the foil with minimal deflection, based on the prevailing plum pudding model. However, the results were astounding. Most particles did pass through with little deflection, but a small fraction was scattered at large angles, some even bouncing back towards the source. This unexpected result led Rutherford to propose a radical new model of the atom. He concluded that the atom's positive charge was concentrated in a tiny, dense nucleus at the center, while the electrons orbited this nucleus. Rutherford's nuclear model, though revolutionary, had its limitations. Classical physics predicted that electrons orbiting the nucleus would continuously lose energy and spiral into the nucleus, causing the atom to collapse. This clearly wasn't happening, as atoms were stable and enduring. In 1913, the Danish physicist Niels Bohr proposed a new model that addressed these limitations. Bohr incorporated the emerging principles of quantum mechanics, a revolutionary theory that governs the behavior of particles at the atomic and subatomic level. Bohr's model proposed that electrons occupy specific energy levels or orbits around the nucleus. Electrons can jump between these levels by absorbing or emitting energy in the form of light. This model explained the stability of atoms and the discrete nature of atomic spectra, the specific colors of light emitted by elements when heated. Bohr's model, though a significant leap forward, was still a simplified picture of the atom. Further research revealed the complexities of the quantum world and the intricate nature of subatomic particles. The development of quantum mechanics in the 1920s, led by physicists like Erwin Schrödinger and Werner Heisenberg, provided a more sophisticated framework for understanding the atom. Quantum mechanics revealed that electrons do not orbit the nucleus in well-defined paths, but exist in a cloud of probability. Their position and momentum cannot be precisely determined simultaneously, a concept known as Heisenberg's uncertainty principle. The atom, once considered a miniature solar system, revealed itself as a realm governed by probability and uncertainty. Further discoveries revealed the existence of other subatomic particles, such as neutrons and protons, which reside in the nucleus. The atom, once thought to be indivisible, unveiled its intricate internal structure, a complex interplay of particles and forces. The journey of atomic discovery has had a profound impact on science and technology. Understanding the atom has revolutionized fields like chemistry, physics, and biology, leading to countless technological advancements. In chemistry, the atomic theory has provided the foundation for understanding chemical reactions, the composition of matter, and the development of new materials. In physics, atomic research has led to breakthroughs in nuclear energy, lasers, and semiconductors. In biology, the knowledge of atoms has been crucial for understanding the structure of DNA, the building blocks of life, and the mechanisms of cellular processes. The atom's legacy extends beyond scientific disciplines. It has influenced our understanding of the universe, from the smallest subatomic particles to the vast expanses of stars and galaxies. It has shaped our perspective on the nature of reality, revealing a world governed by probability and uncertainty. The journey through the atom's history reveals a captivating tale of scientific exploration, from the philosophical musings of ancient Greeks to the complex theories of quantum mechanics. Our understanding of the atom has evolved dramatically. Yet the atom continues to hold mysteries. The nature of subatomic particles, the fundamental forces that govern their interactions, and the implications of quantum mechanics for our understanding of reality are areas of ongoing research. The atom, the fundamental building block of the universe, remains a source of fascination and inspiration. Its story reminds us of the power of human curiosity, the enduring quest to understand the world around us, and the remarkable ability of science to unravel the secrets of the universe, one atom at a time.